Alright, let's answer question 5. Which code fragment will produce a maximally entangled or Bell state? So there are 4 Bell states. Each of them are 2-qubit quantum states. And here's one of them. 0, 1 plus 1, 0 over root 2. Now why is this a maximally entangled state? Well, it cannot be written as the tensor product of 2 separate states. And so because it cannot be written or decomposed into 2 separate quantum states, they are entangled. That's why we call them entangled. Because knowing that Q0, if we know Q0 is a 1, then we know that Q1 is a 0. Absolutely. And if we knew vice versa, Q0 is a 0, then we know Q1 is a 1. Let's contrast that with this valid quantum state, 0, 0 plus 1, 1 over 2. This can be written as the tensor product between state 0 plus 1 over root 2 times itself. So because it can be written, sorry about that, as the tensor product of 2 separate quantum states, then it is not maximally entangled. Knowing that Q0 is a 0 does not tell us if Q1 is a 0 or a 1. And so we're going to figure out which of these A through D gives a final quantum state that is maximally entangled that cannot be written as a tensor product. So here's option A. We have Qiskit initializes qubits in the 0 state upon execution, and then we're going to do an a NOT gate on Q0 and a Hadamard on Q0. Sorry, we're going to do a NOT gate on Q1 and a Hadamard on Q0. So that will create this tensor product. And then let's try to keep, for step 2, the state in its tensor product. Because if we can, then we know it's not a maximally entangled state. So my bet is that we can't. Because we're doing a controlled NOT. It's going to act on one part of the superposition and not the other. Because we want to say an X gate happened because the Q0 was a 1 for Q1, but an X gate didn't happen on Q1 when Q0 was a 0. And the only way to do that is to combine the states. So we'll combine them before we distribute. And then now we can see that the NOT gate will only operate if Q0 is a 0. So we'll just say X gate happened on Q1 since Q0 was a 1. And the NOT gate turns it to a 0. And we can see that this is equal to the state that I wrote up here, which was a valid Bell state. So this is the correct answer. 0, 1 plus 1, 0 over root 2. It cannot be written as the tensor product of 2 quantum states. Well, let's see why the other answers are wrong. So for option B, we take the initial state and we do a C0 from Q0 to Q1. Now because Q0 is already a 0, it won't affect Q1, and we have the effect of the identity. It does nothing. And then we do a Hadamard and a NOT gate like we've done before. Ooh. And that is a tensor product. And so because it's a tensor product and it can be written as the product of 2 states, quantum states, then it is not a maximally entangled state. How about option C? So for step 1, after the initialization, we'll do the Hadamard on the Q0, And on Q1, we'll do a NOT gate. And then we do controlled Z gate on the system. So we'll try to keep it as a tensor product, but like we said before, we'll have to combine it since the Z gate's only going to act on part of the superposition. Sorry, that's a 2. And so we'll write that down here. 1, 0 plus 1, 1 over root 2. And now we can see it won't affect the first part, but it will affect the second. So we'll say the Z gate happens on the Q1, when Q0 is a 1. And the Z gate on the 1 state adds a phase of -1, which is equal to e to the I pi. So e to the I pi, which means we're going to have a relative phase. Sorry, that's all over root 2. But that relative phase doesn't cause the system to be entangled, because we can still decompose this as one qubit in the 1 state and the other qubit in the negative state, which is equal to the Hadamard on the 1 state. So since that's a tensor product, it's not the right answer. How about D? So on for step 1, we do a Hadamard, and then we do a Hadamard again for step 2. So we'll see that that simply causes the 0 state to be mapped back to the 0. Causes that superposition to be mapped back to the 0 state. Essentially inverts the state, because this creates the equal superposition of 0 and 1, and a Hadamard on the 1 state creates equal superposition with a relative phase. And so that relative phase will cause interference with the other phase, and causes the 0 state to combine, or the coefficients of the 0 state to combine. Sorry, I wrote a square root. That's a 1. And so since those will interfere, that'll go to 0, and the amplitudes for this one will go to 1, leaving us with an amplitude of 1. Which this, by definition, is a tensor product, and therefore option D is not the right answer.